Hello and welcome to my video, lesson 7.6 on the mass defect. So mass defect is the difference in mass between the individual neutrons and protons within an atom, the total mass of the atom once they're held together within a nucleus. So basically, when we look at each individual neutron or proton, we can associate a mass with that by itself. Very difficult to separate out a neutron. A proton is not too hard. It's a hydrogen atom without an electron and without any extra neutrons, so it's just a regular isotope of hydrogen. So that's pretty easy, but neutrons by themselves are harder to measure. But over the last 50, 70 years or whatever, we have measured these pretty precisely now. And these values are given in your formula sheet. 1.67 times 10 to the negative 27 kilograms. And they both have the same mass, or at least close enough. There is a mass difference between the two that we might take into account sometimes. And so we'll see that below here. But those are individual masses for each. But once we put them all together, it turns out there's a mass defect. There is some amount of mass that's missing that's holding the atom together in the nucleus. So if it wasn't for this missing mass, that would mean that missing mass is basically giving us energy. And it's giving us energy in the form E equals mc squared. So that missing mass means we have to have energy that the mass is converted into energy. And that energy is holding the nucleus together. This has to do with the strong nuclear force. And this energy is called the binding energy of the nucleus. So the strong nuclear force is the force required to separate out the nucleus or into its parts, or vice versa. I mean, it's either way. So it's the energy that holds it all together. Since energy cannot be created or destroyed, only transformed from one to the other, that must come from the mass defect from E equals mc squared. So from the formula sheet, we're told these different values here, these ones right here, but oftentimes we might want more precise values because there are some differences between protons and neutrons masses, as you can tell right here. A neutron actually has more mass, and that has to do with the fact that it has 2 down quarks and 1 up quark, which will come back to in a later video in the standard model. And the proton has a little bit less mass, but they're very, very similar. Okay, and there's a more precise value for the atomic mass conversion there. Okay, so what is the total binding energy of uranium-235 in mega electron volts if its atomic mass is this? Okay, so what we're looking for is the total amount of energy to separate all of the different nucleons within uranium apart. Okay, so essentially we have to keep in mind that it's uranium-235. So that means there's some amount of protons and there's some amount of neutrons. Now because it's uranium, it's going to have 92 protons. And if it has 92 protons, that must mean that it has 143 neutrons. Okay, so that's important to know because what we're going to do is find the total energy or mass of 92 protons. So proton count or proton mass, which we're going to use 1.67. We're going to use the most precise value that we have, plus 143 times the neutron number, 1.67. Keep our sig digs in our calculator, but we're not going to worry about writing it all out again. All right, and we get the answer of 3.93 times 10 to the negative 25, and this is in kilograms. Okay, now that is the like amount of mass that there is for all of the protons and neutrons. But we also need to know the actual mass. This is actually the atomic mass, not the actual mass. So what we're going to do is take this and also multiply it by the ratio here. That basically is just a conversion, unit conversion that we're doing right now. Okay, so we get an answer that looks something like this. And you can see here that the masses are very, very similar, but there is a slight amount of difference, somewhere around 3 times 10 to the negative 27. We're going to get the precise value difference here. This number minus this number. So we get the difference between the two is, so delta M is 3.09. So I'm going to put 3.1 times 10 to the negative 27 kilograms. Well, if we're looking for the total binding energy, so this is how much it is, like how much the difference is. The total binding energy is going to be E equals mc squared. So we're just going to find E. So it's going to be, this is our M, okay, our change in mass, times 3 times 10 to the exponent 8 squared. And so we get 2.78 times 10 to the negative 10. This is in joules, so we can now change this to be electron volts by just taking that number and dividing by 1.6 times 10 to the negative 19. So now we have electron volts, and then what we do, because we want mega electron volts, is we divide by times 10 to the exponent 6, and I'm just going to put that in brackets just in case. I'm never confident in my brackets, so I want to make sure that I force it to do what I want. So 1741.5 if we want, mega electron volts. So to be more precise, with sig digs, we've got 3 sig digs because of the speed of light having 3 sig digs by the value that we use. So times 10 to the exponent 3 mega electron volts. So there is our final answer. All right, let's see if we can do one more question now. So I recommend you pause the video now and try it out yourself and see if you get the same answer. Okay, so what is the atomic mass of iron 56 if its binding energy is this much per nucleon? Okay, so this is not the actual binding energy, it's the energy per nucleon, not the total, but per nucleon. This is important because iron 56 has 56 nucleons. So if we want to find out the total energy, it's going to be like this, right? And then if we want to change that to joules, what we would do is just multiply that by 1.6 times 10 to the negative 19, which is joules per EV. We get 7.88 times 10 to the exponent negative 11 joules. Okay, so this is now the total energy, not per nucleon. So now we're working backwards. So this is the total energy. So this is our E value, and we're looking for the delta M. Oh, this is going to be annoying. We're looking for the delta M, and then we have to work our way backwards to get the actual atomic mass. Yeah, so it's going to be E over C squared equals delta M. So let's just plug this into our calculator. So negative 28, yep. Okay, so this is our mass defect. So what we need to do now is, that's how much different it is from what you would expect. So what do we expect? Well, now we can kind of figure out what we're actually going to expect, which is if it's iron 56, okay, then we have a certain number of protons and a certain number of neutrons. Iron has 26 protons, so it's going to be 30 neutrons. Okay, now we can do what we did in the last question. I'm just going to write it like this. But we're going to keep all those sig digs in. Again, we're keeping as many sig digs as possible. So this is what we would expect to get. So 9.37 times 10 to the exponent negative 26 is what we would expect to get in terms of kilograms. But we know that it's going to have a mass defect of this much, 8.76. So that means that we have to add that amount back in. So it's going to be, or subtract that amount, I should say. So it's actually going to be this number minus this number. And so when we subtract those two, so it's this number, well, it's going to be the green one minus the pink one. Okay, and so when we subtract those two, what do we get? We get 9.28. Oh, it rounds up to 9 times 10 to the negative 26 kilograms. All right, a lot of calculator work here in this one, but hopefully that makes a little bit of sense. I hope this video helped you better understand the mass defect and what it means to have binding energy to hold the nucleuses together. Hope the video helped, and good luck.